this area. So we are really lucky to have her, and I was trying for some time, and I'm happy to see her here. Professor Mohan.
So the title of my talk is rapid generating distributions. And horizontal curves. So the species that I will be working on are manifolds, which are locally like RN. So the examples are, for example, spheres, and then torus, cylinders, and so on. Now, the notions that become useful in studying manifolds are vector bundles, vectors, for example, and one forms. So vector fields and one forms. So what do they do? Generally, when I given a manifold to each point, which we denote by EXM. So supposing that the manifold is denoted by M, and this is called the tangent space. So a vector field by this correspondence, which takes a point X to the vector is one tangent space. So in this picture, suppose you have a point. So at each point, you have certain directions associated with this. It's not just direction, but one-dimensional lines. So a vector field is a specific vector in the tangent space. On the other hand, when I look at one forms, I will denote it by alpha. Any point X to alpha X, which is an element of the dual of this tangent space. So this will be our objects by means of which we will study the spaces. So vector fields are, I think, you are familiar with. So at a given point, you have certain directions, and alpha is a one form which takes a point to its called a Poolen unit. Now, examples are, for example, if I'm not familiar with the manifold, you can simply think about Rn and vectors. So suppose n is equal to R3 and XYZ are the usual coordinate vectors, then I denote by this the canonical coordinate vector fields. And their dual elements are denoted by dx, dy, dz. Now, what we are interested in are certain distributions. Distributions on manifolds. So this is to each point X on a manifold N, we associate a subspace Dx. Dx is a subspace in the tangent space at that point. So if you have a vector field, for example, suppose X is a vector field, and suppose X is non-vanishing at each point X, then the span of this vector Xx, if I define this with Dx, then X going to Dx is a one-dimensional distribution. So this is an example of a distribution on any manifold given by a non-vanishing vector field. So but Dx in general, so if dimension of Dx is k for all x in n, then we say that D is is a k-dimensional distribution on M. So the second example that one can see here is given by a one form. So suppose alpha is a one form on M. That means at each point alpha x is in the Riemann space of the tangent space. So I can talk about the kernel of alpha x, whose dimension would be one less than the dimension of the n, because it's the kernel of the linear function. So I can define dx to be, and also I assume that alpha x is non-zero for all x in n. So if we have a non-vanishing one form on a manifold n, then I can define a distribution of, we call it the co-rank 1 distribution. So I can define a co-rank 1 distribution on the manifold by kernel of this one form alpha. We can define two classes, one class of vector case, a distribution P on a manifold N is called involutive if given any vector fields. Yes.
That equation xf of x is equal to dfx x of x.
So I will as a smooth function. So what is its value at this point x? This is x small x is the point in N. So I can talk about the derivative. So f is a infinity function on N. So I can take the derivative of this and evaluate on the vector x's. So capital X is a vector field. So capital X small x, this is the point in the tangent space, whereas dfx when I take, this is an element in the dual. Write this on this vector. So a distribution D is called involutive if given any vector fields x, y, which takes values in D, that is your so such vector fields will be called vector fields in D or vector fields taking values in D. So if you have two such vector fields, then given any vector fields, this the vector field, the Lie bracket, also takes values in D. So this is called a involutive vector field. So if you look at this vector field, I know that the Lie bracket of this vector field, so I evaluate on this. This is simply del x, del y on f minus del y, del x on f. But f being infinity function, in particular if it is simple, then this is 0 because the order of differentiation does not matter. So this is an example of an involutive distribution. So whatever is not involutive, we call a non-involutive distribution. The second definition that comes here is the following: that suppose your distribution is not involutive. So it is not, we call this, it's a closed under the Lie bracket operation. Suppose it is not, then you start with vector fields, etc. from B. So this is the shorthand notation that these are vector fields, but they are taking values in B. It's not like this, but this is the formal thing. Then you keep on taking you take all such successive Lie brackets and so on. So because if it is not involutive, then for some pair of vector fields, this xy Lie bracket will not be in D. So it will go outside D. So suppose I keep on taking successive Lie brackets of vector fields that lies in D, and if they are spanned at each point, if span of all these vector fields at each point x in n is equal to exm, then we say that D is bracket generating. Note that D is a proper subspace of exm at each point. But if I take vector fields from D and consider successive Lie bracket operations on them, here, if I take the Lie brackets, if I take the Lie brackets of this is y del del z plus del del x. So del del y operates on y, so this would be del del z, and del del x, del del y, del del y, del del, that will cancel. So you can take the operations and you will see that this is del del z. So already in this space you had these vector fields. And you add this third vector field now. So if you subtract this from here, you get the delta x. So after one Lie bracket operation, you can see that it is generating the whole tangent bundle. So this is an example. So this is an example of bracket generating distribution. So we will be interested in the first one is the involuntary distribution. They come under the foliation theory, and we will be interested in the second class. So there is another criteria. Suppose you have on in manifold. Suppose you have in particular on R3, suppose you have alpha in one form, then alpha with d alpha equal to 0, that will give you the involuntary distributions. And if you have alpha with d alpha non-zero everywhere, then this gives a bracket generating distribution. So you can use the Karta formula to get this observation. So what it does, so our space is a manifold together with the distribution B. B is bracket generating. We will be working in this structure. So what are the admissible maps that we have to discuss first? So a curve now N, so we denoted by this, is said to be horizontal. By horizontal, I mean horizontal to the given distribution D if its tangent vectors lie in the distribution. So if you are given one associate, suppose certain spaces at this point, here of course it's two-dimensional, but there is nothing to prove. But suppose you have a vector. So if you plot some vector field like this, so the curves that is allowed here will be, whenever it will be hitting a point here, it should be tangential with distribution. That's a very bad picture. So if gamma prime T belongs to T. So these are called horizontal. Similarly, this notion can be extended to other domains as well. So the horizontal immersion is suppose a map A from some manifold sigma into N. This is an immersion, and its derivative at any point this maps the tangent inside the. So if you have this infinity immersion means the derivative map at which point is injective linear map. So if you have an immersion which takes the tangent space of sigma into the distribution D, then we say that is a d-horizontal immersion. So these will be the admissible maps for us when we will be working on a manifold distribution. So why these are important? Charles' theorem says that suppose D is a bracket generating distribution. On a manifold N, then if you have given any 2 points, say P, Q, these are points in N, then there existed a smooth curve gamma from I to N such that gamma 0 is P, gamma 1 is Q. That means you can join this point by a curve, and gamma is horizontal. Of course, if your manifold, if you start already with a manifold which is connected, you know that any 2 points can be connected by a path. But here you have certain constraint motion. You cannot allow all paths. You are only allowing paths which are horizontal to a given distribution. So the distribution is given. The question is whether 2 paths can be joined by a horizontal path. The Chow's theorem says that if D is bracket generating, then you can do so. So this is an important point in the study. You can say that this is the starting point of the theorem. Also, the second.
Is this the same Chow's theorem which leads to Chow proof? Gannon's paper, the same thing?
I'm not, but probably not. So the second one, which was proved much later, the next question that comes is that suppose you have a path, this is an arbitrary path, gamma, joining 2 points. Is it possible you have a horizontal path which lies very close to gamma? That means density of the space of horizontal curve. So we said to prove that if D is bracket generating, then any path joining 2 points can be approximated by a horizontal path. So these are 2 theorems. But let us explain this in the context of, say, contact distribution. So there, the form is given by this and its kernel. So if alpha, so if gamma is horizontal, so I can write gamma t as xt by t. And if gamma is horizontal, then gamma prime t will be in the kernel of this, which says that this dz dt is equal to yt, and this is x. So the question which is addressed by Chow's theorem is, suppose you have 2 points, say P and Q, and let this is x naught, y naught, z naught, and this is x1, y1, z1. Then whether you can draw by some join them by some curve which satisfies this differential equation. Okay. So if I take the curve, the first coordinate being t, and then this is yt, zt, then you can see that you And if you integrate, then Z1 minus Z0, you integrate this. It's very easy to find a curve Y in terms of T between T0 and T1. This is the area under the curve. So this area under the curve is given. So you can draw some pictures in the two-dimensional and you can see that this is a easily solvable problem. So whenever you have such a solution, that will give a horizontal curve by this solution. Now, also you can address the Bayes theorem. So here is an idea. Suppose this is the z-axis. Now this z-axis is of course not a horizontal curve. So the question is whether you can have a horizontal curve which is very close to, which is in the C0 neighborhood. So you can try with this cos t sin t with a very small radius, and you find appropriate zt such that this becomes horizontal using the same equation that we have written down. So these are easily explainable on 3 contacts. Now the next question that is relevant here is does there D is bracket generated? Does there exist a horizontal immersion F from S1? See, earlier we were saying there are lots of curves joining 2 points. So I can join 2 points, P and Q, by some horizontal curve down. And there are plenty of curves as by Bayes theorem. So you can also take another curve joining these 2. But if you concatenate them, the points P and Q will not be smooth. Okay. So here the question is, this is of course a loop. This is a continuous loop, but this is not smooth. The question is whether you have, say, a smooth curve which is horizontal and which is also a loop. Also, this immersion condition is important because otherwise you can reparameterize this continuous curve to make it smooth. But the derivative at these points will vanish. So, because you reparameterize the curve in such a way that the derivative dies down at these points. And then again start very slowly to come back to this point around this. So that is possible. So I want to eliminate that. So the question now can be reformulated as whether there is a smooth immersion which is horizontal. And also whether an embedded horizontal loop. Now these questions have a very satisfactory answer. It says that given any continuous curve in the Bayes manifold, up to satisfaction, okay, I'll come to that later. But I just want to say that the first question, question 1, has a satisfactory answer in the form of H+. I will not go into this, but what about question 2? So here, what I want to say is this: suppose you have some space of maps between manifolds. So any smooth map that gives rise to a map between their tangent bundles. And so if this says that this is horizontal, horizontality means that it takes the tangent spaces into, suppose you have A with a distribution D, so this is in dx. So naturally, if I replace dA by an arbitrary bundle map, which takes dx sigma inside some d fx, I can talk about these maps. See, not all these maps which are defined at the bundle level may come from a smooth map from sigma to n. This is called a formal solution. Or we can say formal horizontal map. So here I demand that there is a fiber-wise injective linear map between the tangent bundles, which takes the tangent spaces into D. So they are called formal horizontal map because they do not necessarily come from some f as a df. So the H principle means that it asks the following question. Suppose you know that there exists such a bundle map. Can you conclude that there is a smooth map like this? See, this is a very easy question to address because this is in the realm of algebraic topology where you have the obstruction theory to address this problem, and you can to some extent say that okay, there exists or there does not exist, there is some obstruction to having such things. Of course, if you can show that there does not exist any such bundle map, such a thing cannot exist. But what happens when such a bundle map exists? Can you conclude from there that there is a smooth map? This is what H principle says. So when I say that this is a satisfies H principle, that means whenever you have a formal horizontal map, you can deform this formal horizontal map to an actual horizontal map, which is smooth. So this is a theory by Gromov, known as partial differential relations. This is a book in which there is a detailed study of this. So here also, in case of this horizontal inertials, one can show that if there exists such a bundle map which is fiber-wise injective and which takes the tangent bundle inside the distribution D, then I can homotopy it to a horizontal. And what happens in the case of embedded horizontal loop? So this what I have said in this context is only for S1, but it is true for arbitrary manifolds as well.
That map is continuous?
This one, yes, this is always continuous. Yeah. This is a continuous bundle map, fiber-wise injective. Now what happens to the second question? So in fact, it was shown that this sort of thing is not true for we showed that infinity horizontal. So you cannot deform that formal horizontal embedding to a actual horizontal plane. So this is called the rigidity theorem. And the first one, which I referred here, this is called flexibility theorem. So whenever something formal can be homotoped to an actual solution, we call this a flexibility kind of result. And when it cannot be done, we call it a rigidity result. And this actually generated a lot of activity in the field of quantum structures. And many people contributed to this area, starting with Elias Schwab, many others.
But you mean topological embedding, formal horizontal embedding?
No, this is not all. This when I say formal horizontal embedding, this is slightly more than this is not just. Okay, I will. If I have time, I will explain this.
By correspond, you mean homotop or?
Yes, more. By correspond, I mean can. I will also touch upon another. What's the time? Another distribution which is known as angle distribution. This is also very specific. This appears on R4. So very specific to R4. And you can define this by pair of forms. So the coordinates here, I take x, y, z, w, and these are 2-1 forms. If you look at the common kernel of 2-1 forms, see each kernel will give you a codimension 1 distribution. And if these 1 forms are independent, then their common kernel is a codimension 2 distribution. So you look at, so if I call this alpha, if I call this beta, then the distribution is kernel alpha intersection kernel beta is a 4-dimension 2 distribution. That means at each point is associating a 2-dimensional subspace. Why this is interesting? Because this distribution appears in certain mechanical system. In what way? Suppose you have a 2-dimensional plane here, and you have a plane, just a round-shaped plane, which is located touching this plane, as this is in the vertical direction. So this is the point of contact of the penny with the xy plane. So this is the xy plane where the penny touches the. Now suppose you allow this penny to roll on the surface. So this can be described, the motion of the penny can be described by 4 coordinates. One is the point of contact, which is xy. Then suppose you take some fixed point on the rim of the penny. Suppose they call. So basically, you look at if the penny is allowed to roll without sliding and keeping it vertical to the xy plane, then what is the locus or what is the motion of the point P? Then of course there is a center of the penny. So you have to join this and you have to see what the angle it is making. Suppose this is phi, and then you have to see the another angle psi, which is the angle between the plane of the penny with some x-axis. So suppose the penny is making some angle. So this is the angle, so this is psi. And this one would be phi. So by these four coordinates, we can describe the motion of the penny. That means the motion of it. Now, if I look at this, then of course there will be certain equations of motion. And you can see because equations of motion can be written in this form. So, if you say that whether there are two positions x, y, phi psi and x1, x prime, y prime, phi prime, psi prime, whether a penny can roll from one position to another, that is simply the integral curve of this. So if you can join these 2 points curve to this distribution, then you can say that the penny can roll from x, y, phi psi position to x prime, y prime, phi prime, psi prime position. So this angle distribution is closely connected with this mechanical system, and that's why it's interesting. So I must say that here, this problem is the similar problems for horizontal immersions and embedded loops were also solved by this is a recent Parsons and that the horizontal loops other than what is non-rigid? So rigid loops are those which are, you can see that if you look at the kernel alpha, this has at least one vector field is del del W. So this is in the kernel. There are of course another vector here, but del del W is a vector field. So the integral curves of del del W are called rigid loops. So this may be misleading because here we are working in R4, but this can be an arbitrary manifold where you may get some loops. This is a picture in the local modes. The integral curves del del W, not in this context, by the way. Very small. Rigid curves. So these are two important distributions in low dimension. One we have discussed in dimension 3 and another in dimension 4. So in the general situation, however, the integral curve problem is basically a ODE kind of problem. Right? But in higher dimension, this will define a system of partial differential equations. So the solutions will appear as a solution to a PDE which is given by a differential operator. Now what are the questions that, so you have MD, the D is bracket generative. The first question is this, that what is the maximal dimension of an horizontal submanifold to a given point. So you have a manifold M together with a distribution. So at each point you have certain planes, and the question is, given a point P in manifold M, what is the maximal dimensional sigma that you can get, which will be horizontal to the distribution D? So in the first example, you recall, this is the kernel of dz minus y dx. We considered curve. This gives a two-dimensional distribution. It cannot have a two-dimensional horizontal submanifold. Then it would be involutive distribution. Because it's a, so that is the maximum dimension of a horizontal thing that can appear in this. But in a general situation, what is result? So if again I take M with xi I usually denote by the contact structure. So in the higher dimension also we have a notion of contact structure, but only on odd dimensional manifold. So xi can be given by kernel of alpha, where alpha satisfies so whenever I write non-zero, I mean non-vanishing at each point. So these are very important kind of distributions. Why? One of the reason is that they appear in many contexts, of course. But even otherwise, they are generic. That means if you look at the odd dimensional cases where you are looking at 4-dimension 1 distribution, generic means they are form a second category set. So there are plenty of such objects. Even in the case of Engel, in R4, when you are looking at the 4 and 2 distributions, Engel distributions are generic. So you are basically looking at a very specific distribution, but they are in abundance. So in case of this, if you look at, so here there are many results which are known, and the answer to this question is this. For contact structure, the maximum dimension of a horizontal submanifold, I mean local, is n. This can be actually checked by some linear algebra. Because what happens if you look at the kernel of xi, which is the distribution D, then if you look at D alpha and restrict it to D. This is a 2 form on D, and this condition says that this 2 form is non-degenerate. So this is non-degenerate. And immediately the linear algebra implies that it can have at most n-dimensional isotopic subspace. So let us look at this. Suppose F is horizontal. Then this is defined by alpha. So if something is horizontal, then we say that dfx of some vector is this belongs to kernel alpha. So if I apply alpha on this vector, I should get 0. So this is equivalent to saying that if I pull back the form alpha, by F, you have the form alpha on this space. If you pull back this form, then if it is horizontal, you can only F star alpha is 0. And then if you differentiate, this is the exterior operation. This is also 0. That is, you can interchange this. This is called the isotopic condition. So whenever you are starting with this condition, you additionally get this. And this is a kind of obstruction. So we have to take into account this obstruction when you look at H principal type result. So in this equation, your formal map will be this, that you will have a bundle map from P sigma to Tn. Of course, this is fiber-wise injective, which will pull back F star alpha to 0. Not only that, this will pull back F star d alpha also to 0. These two conditions, this is called a formal horizontal map. And then the result of H principle says that formal horizontal map can be homotopy to an actual horizontal map. And this can happen in dimension n at most. Now you can see here that generally, if you are at the formal level, if you are given only this F star alpha, you do not get this. You get only if you have this differentiability criteria. But on the other hand, so you might ask, what happened to the case when we are considering the one-dimensional problem? That means the horizontal loops. I did not write this equation there because it is automatic. In one-dimensional, because you are considering a two-form, any one-dimensional direction is automatically isotopic. So this condition did not appear here. So these theories are more or less understood by the 80s, and the problem of invaded So invaded Lagrangians means this is the top dimensional horizontal submanifolds in your contact. This is specific to one. So what happens? So already we have observed that in dimension 1 did not satisfy the H principle. But in higher dimension, things are slightly more favorable. So there is a recent result by Amy Murphy. So she proved that there is a class of Legendrians, loose Legendrian. So this is very technical. So Legendrian satisfy H plus. So there is a class of Legendrian embeddings which behave nicely in terms of H principle. That means if we have a formal loose Legendrian, that can be homotopy to an actual Legendrian. So at the end, I will just say a few words about. So as you can see, we have discussed only mostly 4-dimension, only the contact structures in the details, and there was one very specific angle structure on R4. This is a 4-atom distribution. So what happens to other situations? Do we have a complete classification of them? The general theory of Gromov says that we can classify them provided certain conditions are satisfied. But what happens in general? So we looked up the following problem, and basically these are comes in the context of a right holomorphic contact forms and their analogs. We will be working in the C infinity setting, but the origin is in Cn. So as you recall that here any one form alpha satisfies this condition is called a contact form. Exactly the same thing for the holomorphic contact form. Suppose you are working in Cn, you have a holomorphic Watt form, and this condition is satisfied. Then I say that this is a alpha is a holomorphic contact form. And there is we have identified some C infinity analog of this. And there is another class which is quaternionic. Contact forms. And they, of course, this gives a 4 and 2 distribution. And this gives 4 and 3 distributions. So in this context, we could completely classify horizontal immersions in the above context. But there we need with an additional regularity condition. So this was a joint work with one of the results I just quoted. So it says that suppose M is a manifold with a distribution D where 4n of D is 2. Okay. And so 4n D is 2 means D can be written as kernel alpha intersection kernel of beta. And we assume one specific condition to D which is also shared by the contact form. This is called strongly bracket generated. So what we saw in the case of contact forms, when I start with alpha, which is a contact form, and D alpha I restrict it to D, then this was a symplectic form or non-degenerate form. So there is a class of distributions which are called strongly bracket generating. So they are defined by, there is a restriction on K, we'll come to that later. So D can be written as common kernel of certain number of forms such that, or sorry, D is a distribution such that every annihilator of D by T satisfies D alpha restricted to D. So this class of distributions are called, sometimes called fag distributions, sometimes called strongly bracket generating distributions. Now contact distributions, holomorphic contact distributions, and their analogs and quaternionic contact distributions, they all satisfy this fatness condition. And in that case, many nice things happen. So using that, we could prove that so D is this is the analog thing that I'm describing, degree to 4 and to distribution, then regular horizontal immersions from sigma n satisfy the H principle if the dimension of n is greater than or equal to 4 times dimension. And this dimension is this is the optimal dimension. This cannot be improved. So whenever in this context you can produce a formal horizontal immersion, you can conclude that there is a genuine horizontal immersion.
Is there any question?
Regarding that bracket generating hypothesis that it's not it. I mean, I have an intuitive picture. So if you just take del by del x in R3 or R2 or something, and you want to, let's say, start at x-axis and reach somewhere the y-axis, like you can't do that. So it will be nice if there is a del by del y in the distribution, but what Chow's theorem is saying is that a vector field whose rate of change is in the direction of y would also suffice, which is what the bracket is capturing, right? With the v derivative.
Basically, it must have components in various directions.
Yeah.
It's not just in one coordinate directions.
So what I'm saying is the bracket coming up there is probably capturing a v derivative of the vector fields. So that is the only reason I could think of why.
Bracket appearing where?
So in that hypothesis, you said if the distribution is bracket generating, if it generates the whole bundle,
Yes.
then
So
you
you
can
can
join any
reach,
two.
yeah.
Any two points.
So this basically says you have certain fixed directions to move. But even then, can you reach any point? That's the general real problem. So it is giving certain condition on that. And actually it appears that they are plenty. It's, except for some small subset outside this, most of the distributions that you will get is bracket generated. That is clear because involutive means it's given by some equation. But these are all inequalities. So inequalities gives you plenty of things. Maybe this is not answer to your question.
That's okay.
Any further question? So, is there any question from the online participants? So you can unmute yourself and ask the question. Doesn't seem like. So let's thank Professor Mohammed. So, what time we? At 11 we assemble again. A small break.
That is also related to something called curvature of the distribution.